Now that we know how to differentiate with inverse trig functions, we want to make sure we can also integrate with inverse trig functions. So I want to point out that this is all review from the last video you've watched. All I did was rewrite all my derivatives of my inverse functions. The reason I wanted to do that is I wanted to point out where the inverses of the inverse trig functions come from. So notice that if I were integrating u prime over the square root of 1 minus u squared with respect to u, if I were integrating this here, I'm going to get back the function I had before differentiating. So if I were to integrate this, I would just get arc sine, I'm not going to have enough room, arc sine of u plus some c. Well, notice if I were integrating this, these match up extremely close. Couldn't I just pull the negative out front and say it's the negative arc sine of u plus c? That, to me, is easier than having to know 6 different integrals. Because the other thing I could do is I could say, well, this just integrates to be arc cosine of u. But why have to know 6 if all I really need to know are 3, because I can yank out the negatives? Same thing with arctan and arc cotangent. I can pull out the negative and they match. With arc cosecant and arc secant, I can pull out the negative and they match. So I'm going to go ahead and I'm going to say that rather than have to memorize all 6, this is just the negative of arc sine u plus c. So for that reason, even though we have 6 derivatives, we only have 3 integrals involving inverse trig functions. So we have the derivative of, and notice that up here I always used a 1. Well, what happens if I have a number other than 1? So what happens if I have du over a squared minus u squared? Well, that's going to anti-differentiate to be arc sine of u over a plus c. The integral of du over a squared plus u squared is 1 over a arc tangent of u over a plus c. And the integral of du over u times the square root of u squared minus a squared is 1 over a arc secant absolute value of u over a plus c. I tend to, in this next, if you look at your in class when we do our next homework assignment, I tend to write these at the top of all the sheets that I use. So if I flip my page over, I rewrite these all at the top. The reason being is because we are going to often try to use u substitution because we can't integrate the way something's written, and u substitution isn't going to work for us. But what we might be able to see instead of u substitution is that we can make our integral look like one of these 3 functions, because if they do, then I can integrate it to be arc sine, integrate it to be arc tangent, or integrate it to be arc secant. So let's look at some examples where we do that. I think if I remember right, there's 4. So looking at the first one, I have the integral of dx over 4 minus x squared. So the first thing I might try to do is I might try to say, hey, I'm going to let u equal 4 minus x squared. Well, then du dx ends up being negative 2x. And the problem I run into, I don't have the negative 2x. I can't insert a variable. I can only insert numbers. So that doesn't work. So I'm going to go ahead and, oh, I can't erase that. I'm going to go ahead and color over it in white and see if that'll work for me. So that didn't work, so erasing that, I'm going to try something else. What if I check to see if this is in the form of one of my functions here? Let's see if I can keep them on the same page or on the same screen. Well, I see that I have 4 is a perfect square, so my a could be 2. My u could be x. If my u were x, that means my du could go in for dx. And I could rewrite this as the integral of du over the square root of a squared minus u squared, which I know integrates to be arc sine of u over a plus c. Well, my u was x, my a was 2, and my c is some constant. So there would be what I would get when integrating this function. If I go ahead and look at my next example, and I'm going to lose these because I'm not going to be able to keep them in the same screen. So I'm going to be referring to these, even though visually they're not going to be on the screen. So I would keep these handy with you when you're watching this video. So in example 2, I would do the same thing. So you're going to start to see kind of a pattern, so I won't do this on all of these because this will be a crazy long video. But if I let u equal 2 plus 9x squared, which would probably be my first start, I'm going to anticipate that du is going to be 18x. And I cannot get that extra variable in there. I can't get the x in there. So instead, I'm going to see if I can rewrite this in a way that it matches one of my inverse trig functions. Well, 2 isn't a square, isn't a perfect square, but could I say that a is still the square root of 2? And perhaps I let u equal 3x. Well, then du would be 3 dx. So just like before, very similar to u substitution, I'm going to have to get a 3 in here, which means I'll have to put a 1/3 outside, giving me 1/3 times the integral of 3 dx over 2 plus 9x squared. Changing it with these things here, I get 1/3 times the integral of du over a squared plus u squared. Well, I know that this integrates to arctan. If you look, then your integral of du over a squared plus u squared is 1 over a. I got to keep the 1/3. Arctan u over a plus c. Well, my a is square root of 2, my u is 3x. So I end up with 1 over 3 square root of 2 arctan of 3x over the square root of 2 plus c as the function that this integrates to be. Looking at the third example. On example 3, same thing. Notice that if I tried to let u be x, du would be 1. I'd have this here that I'd have no idea what to do with. If I tried to let u substitution and u be 4x squared minus 9, I'm going to anticipate that my du would be 2x. I don't have a 2x. I have a 1 over x, but I don't have a 2x. I have no way to get that 2x in there. So I'm going to see if I can't make it look like one of my trig functions. Well, if I'm looking at my list of trig functions, notice that my integral that gives me a function involving arc secant is the integral of du over u times the square root of u squared minus a squared. So I'm going to try, and I'm going to let u equal 2x and a equal 3. Well, I'm going to write down that integral that I'm using. I'm using this one right here. Okay. This is one of my formulas. Well, if I let u be 2x, which I have to let it be 2x, this is the only way to get 4x squared. I don't have u on the outside. I only have x on the outside. But don't I know how to get numbers in? Couldn't I sneak a 2 down here? So if the 2's on the bottom, so technically a 1/2 in here, couldn't I adjust that by putting a 2 out front? So I'm going to go ahead and do that. I'm going to say that this function here that I'm given is the same thing as 2 times the integral of dx over 2x times the square root of 4x squared minus 9. Okay, so I have that. So I know my u, I know my a. Now I have to figure out what my du is, because if I'm going to plug those in, if I look here, I also have to have a du on top. Well, if u is 2x, that must mean that du is 2 dx. Well, I need the 2. How do I get a 2 on top? Well, now that I'm a little bit further, I see that I maybe did some stuff I didn't have to do. How do I get a 2 on top? I put a 2 on top by putting a 2 underneath. So notice that in hindsight, I could have just put a 2 over 2 here and didn't have to put anything out front. So now I get the integral. I'm going to go ahead and know that out front I have a 1, so I don't have to write it. 2 dx becomes du. 2x is u times the square root of u squared minus a squared. That integrates to be 1 over a arc secant absolute value of u over a plus c. Well, I know that my a is 3. I know that my u is 2x. and my c is a random constant, so that stays c. And that will be, my plus sign is not looking very good, and that will be my final answer for example 3. Looking at example 4, I lied, there's 5 examples, I thought there were 4, I apologize. Looking at example 4, I'm going to do the same thing. So again, if I were to try u substitution, 4 minus x squared, if I let that be my u du is going to be negative 2x. I can't get an x in here, so I have to try something else. Well, I noticed that in terms of my integrals, this is really close to this integral. The integral of du over the square root of a squared minus u squared. Super close to that. If I can get it to match this, then I can integrate and it'll be an inverse trig function. So I'm going to let a be 2. I'm going to let u be x, in which case du will be dx. I'm going to change these so that after I finish integrating, I don't have to plug anything in for u. So I'm going to say that when x is 0, that u is also 0 by plugging 0 in here and solving for u, which doesn't take a lot of work. If x is 1, u is 1. So this integral is going to become the integral from 0 to 1 of du over the square root of a squared minus u squared, which becomes arc sine of u over a, and I don't have to say the plus c, and I'm going to go from 0 to 1. Here's the deal. Because these are in terms of u, I have to plug my 2 in for a, but I don't have to plug anything in for u. So I just get arc sine of u over, what did I say it was, 2, from 0 to 1. So then that's going to now, I'm going to go ahead and use my fundamental theorem of calculus to figure out what this gives me. I have arc sine of 1/2 minus arc, sine of 0 over 2. Well, that's going to be 0. I don't have to worry about this piece here. But what does this mean? This means if I go to my unit circle and I look between negative pi over 2 and pi over 2, what rotation gives me an x value, or excuse me, it's sine, so a y value of 1/2? Well, I get a y value of 1/2 when I rotate pi over 6. So this gives me pi over 6 minus 0, which is just pi over 6 is my final answer. Looking at example 5, I'm going to do the same thing. Well, I noticed that on example 5 that it doesn't fit any of my formulas that I was just looking at, any of my inverse trig formulas, because my u has to be the thing that's being squared with the variable. So this would have to be my u. And I know that e to the x squared, because when I have power to a power I multiply, is the same thing as e to the 2x, but I can't have u minus a. So I'm going to try to use u substitution, and it might get a little bit crazy at first. So I'm going to let u equal, and I'm remembering that this is the same thing as dx over the square root, I don't know if I can write small enough, e to the x squared minus 1. So I'm going to try and let u equal e to the x, okay? And you probably may not come up with this right away, and that's okay because you can spend some time guessing and checking what your u is going to be. But for time-wise on the video, I'm gonna guess the right u right away. So I'm gonna let u equal e to the x, and then du over dx, using that generic u substitution we've used before, equals e to the x. So du equals e to the x dx. Well, this causes somewhat of a problem, because didn't I just tell you that I can't force an extra variable in? I can only put in extra numbers. But lucky for me, e to the x is u. So that means that du equals u dx. Or in other words, du over u equals dx.